Hello, students. So, what I begin today is a very long section in the notes. It will, well, if this were normal time, this would represent 2 or 3 days worth of lecture. I'm going to be cognizant of that in timing. I've set aside at least 2 days in the schedule to think about this stuff. Anyway, so it's about uniform continuity. So here's what this section will consist of. First, we'll spend some time motivating uniform continuity. That is, we'll notice some things that continuity won't do for us. Continuity is a nice property to have of functions. Functions that are discontinuous, hopefully have some other property that you're using to study them. Otherwise, they can be totally wild. It's hard to prove anything. So we'll use that to motivate uniform continuity. We'll provide some examples and non-examples of uniformly continuous functions. We'll prove an important result, which will say that lots of functions are uniformly continuous. In particular, if you have a continuous function defined on a closed bounded interval, or more generally a compact set, if you watched the lecture notes about compact sets. Any continuous function on a compact set is uniformly continuous. And they preserve lots of properties. Uniformly continuous functions preserve boundedness. Uniformly continuous functions preserve Cauchiness. And as a consequence, we'll be able to address something like this question 3.8.1, which really is a property, something that you might ask about continuous functions. Let's let U be a subset of R and F from U to R be continuous, so consider a continuous function. Let P be a limit point of view. Does it follow that the limit as x approaches P of f of x always exists? Well, there's certainly one circumstance it does. We proved ages ago that if a function is, if this point P is in the domain of the function, well, then the function has to be continuous at that point, if it's continuous on the whole set. So not only must the limit exist, the limit must agree with f of P. So as long as P is actually in the domain, yeah, the limit as x approaches P of f of x has to exist. What if P isn't necessarily in the domain? So let's begin by just reminding ourselves, what does continuity mean? So let's recall a definition. So let's see. We say f from U is the name of the domain usually, is continuous if what? So I want you to take a moment and write out the definition of continuity. So pause the video, come back. Okay, good, you did it. So I'm going to write down the definition of continuity right now. A function is continuous on a set U if, and here's like the cheeky answer, for every point in that set U, f is continuous at P. And you say, well, yeah, that is what we define continuity to mean. But what does it mean for f to be continuous at P? Well, this means for every P in U, now expand out f is continuous at P. For every epsilon greater than 0, there exists a delta greater than 0 such that for all x in U, if the absolute value of x minus P is less than delta, then absolute f of x minus f of P is less than epsilon. So let's just, I'm going to continue this aside for a little bit longer, because I think the following will be useful. So let's suppose you wanted to prove a function is continuous. How to prove that a function f is continuous? Well, like the formal logic here tells you how the proof should go. You need to prove something is true for every p in u. So you should start with the line consider any p in u. Next, you need to prove something is true for all epsilon bigger than 0. So you need to consider any epsilon bigger than 0. So you need to consider any p in u and epsilon greater than 0. Next, you need to come up with a choice of delta. You need to show that there exists a delta which satisfies some properties. Come up with delta. And how you do it will depend on the information you're given, what situation you're in. But once you come up with that delta, next you need to show that something is true for every x in u. So consider any x in u. You want to show if this, then that. How do you prove an if-then statement? Well, you assume the hypothesis, prove the conclusion. If that's a capital, then there should be a full stop there. And then, again, this will be dependent on what sort of information you're given. You will now need to show that, using the choice of delta presumably somehow. So I want to emphasize this line right now. So when you come up with the choice of delta, maybe you're given a formula for the function, then maybe you can come up with a formula for delta. Let's think about what this delta can depend on. So it can depend on anything that comes before it. So this delta can depend on p and on epsilon, but it cannot depend on x. X is defined in the line after that. Not on x. So the idea of uniform continuity, it'll be a while before I actually give the definition. What if this delta depends only on epsilon? So the idea is that the way delta depends on epsilon measures like how continuous it is at the point p. So if you can use the same delta for every p, so if delta is independent of the choice of p, then the continuity of the function is uniform across the domain, hence the definition of uniform continuity. So just keep that in the back of your mind. We'll come back to the actual definition in a little bit. So let's think about this question 3.8.1. Let u be a subset of R, and f from u to R be continuous. Let p be a limit point of view. Does it follow that the limit as x approaches p of f of x exists? Well, let's try this. Here's a function, f defined from on the interval from 0 to 1, defined by f of x equal to x squared. So maybe we'll just look at a graph. So that graph is given by something like that. So let's just look at a picture to try to come up with the proof. So let's start with this. What are the limit points of this interval? So let's see. Limit points of 0, 1. Well, we've seen that 0, 1 is a closed bounded set. Such things contain all their limit points. So that means that if p is a limit point of 0, 1, then theorem 3.1.5 applies, and we conclude that the limit of this function f of x as x approaches p is equal to f of p exists. What if the domain's just a little bit smaller? Let's check it out. Let's try to do the same thing on the open interval. So that's changing the graph of the function as follows. Well, let's continue to just kind of come up with an idea of a proof. So what are the limit points of 0, 1? Well, the limit points of 0, 1, so right, what does it mean to be a limit point? It means there's stuff in the set very close to you. So that's a limit point of the interval from 0 to 1. There's the interval from 0 to 1. This is the limit point of that interval because no matter how close you look to that point, you see stuff in the set. 1 is also a limit point. 0 is also a limit point. But notice each of those have the property that you can take the limit of this function at that point. And in fact, this comes from the fact that, well, x squared is continuous. So the limit of this function, f of x, will be the same thing as the limit of the function x squared is p squared, so it continues to exist. So this function satisfies, so let's just state the answer. So the answer to question 3.8.1 is yes. The answer to question 3.8.1 continues to be yes. That might make you think, well, maybe it's just true always. Well, here's two additional functions. F of x equal to 1 over x. And I'm going to use the domain 0 to infinity. So there's the graph of that function. Notice I'm not drawing this bit of the graph because I'm only interested in the domain 0 to infinity. Well, is there any place where you can't take the limit of this function? Yeah, how about at 0? And 0 is a limit point of this domain. So let's see why. So let's see, as x approaches 0, f of x gets big. I won't write down a formal proof. So in particular, f of x is not getting close to a single number. Limit as x approaches 0 of f of x does not exist. So that means this sucker says that the answer to question 3.8.1 is no. How about f of x equal to x divided by absolute value of x, also known as the sine function? So this is the function which is 1 when x is positive, negative 1 when x is negative. So here's the graph of the thing. 0 is not in the domain. If you want 0 to be in the domain, then you can put it there. You'll just fill in a solid dot there. I won't. So let's take a look at this function. What's the limit of this function as x approaches 0? Well, from the right it looks like it wants to be 1. From the left it looks like it wants to be negative 1, but those two will need to agree. So let's see, the limit as x approaches 0, and again I'm going to be a little bit informal, of f of x wants to be 1 and negative 1, but it can't. So limit as x approaches 0 of this function does not exist. So, again, the answer to this question is again no. So in general, the answer to question 3.8.1, let's see how it's written. Let u be a subset of R, let f from u to R be a continuous function, let p be a limit point of u. Does it follow that this limit exists? So does it follow would be asking, if you know all of this is true, then do you definitely know that the limit exists? And the answer is no. The functions 1 over x and sine of x are counterexamples. Nice. So, the idea of uniform continuity is, when is the answer to question 3.8.1 yes? That's what we'll be trying to do. So, I'm going to repeat something that I said earlier. In order to illustrate what the definition of uniform continuity should be, let's just remember what it means for a function to be continuous. A function is continuous means for every point in the domain, f is continuous at that point. So that a should be a p, right? One should be consistent. Those two should be the same thing. If you expand out the definition of f is continuous at p, you see that this means that for all p in u, for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in u, if the absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p is less than epsilon. I should have written a little bit smaller, shouldn't I have? So if you check this out, what variables can delta depend on? As we pointed out already, delta can depend delta depends, can depend. Delta can depend on epsilon and on p. So the idea of uniform continuity is that maybe you can get nicer behavior out of continuous functions if the delta depends only on epsilon. So let's think about the functions that we just studied, 1 over x and the sine of x, sine with a g. Let's see that these things are not uniformly continuous. And it's a little bit silly to show that something's not uniformly continuous. I haven't written down the definition of uniformly continuous. But here is roughly the definition. A thing is uniformly continuous if your delta depends only on epsilon. And we'll state the definition in a little bit more formally. But for now, let's just go through the proof that you've seen already, that 1 over x is continuous, and that sine with the g of x is continuous. Let's just write down the proof. So let's do it. Let's show that f of x equal to 1 over x is continuous on the interval 0 to infinity. So that means you need to prove this statement. So you should start by considering any element of the domain. It doesn't matter if you call it p. I'll call it a, just because, well. Then you have to consider any epsilon bigger than 0. You have to come up with a delta. And this is a situation where you have a formula for the function. Whenever you have a formula for the function, you might hope to get a formula for your delta. Let's let delta be, I don't know, we'll figure it out. Let's let x be in the interval from 0 to infinity, and assume that the absolute value of x minus a is less than delta. Then using the fact that a is bigger than 0, right, by assumption, we see that, well, 1 over x minus 1 over a, that's the same thing as a minus x divided by x times a is equal to, and let's see, you could distribute the absolute value of ours. Absolute value of a minus x divided by absolute value of x, absolute value of a. And, well, notice, not only is a bigger than 0, x is also bigger than 0. So I don't need those absolute value bars in the denominator, do I? Now, absolute value of a minus x by assumption is less than delta. So I'm going to do something wrong right here. So after all of the simplification, you might say, cool, here's what I'm going to do. I'm going to take, I want this to be equal to epsilon. So let's just set that equal to epsilon and see if we can, like, solve. Of course you can. It's easy. You'll get delta equal to a times x times epsilon. But let's take a moment and think about that. Is that actually an okay choice of delta? Delta is allowed to depend on p, which, well, in this case is called a. So it's okay that there's an a there. It's allowed to depend on epsilon. Oh, but x is declared after delta. X is declared after delta. Let delta be blank, let x be in here. Delta can't depend on x. So this isn't an okay choice of delta. So writing this down now more formally, you might now be tempted to set delta divided by a times x equal to epsilon, so that delta is equal to a times x times epsilon. So this delta depends on epsilon, which is fine, and a, which is fine, and x. But that's bad. Delta isn't allowed to depend on x. So whenever you see the situation where delta wants to depend on something that it can't, let's just try to get control over, there shouldn't be any absolute value bars there. There at least don't need to be absolute value bars there. Let's try to do this. If we can get x to be greater than some positive constant, constant as in depends on epsilon and a, but not on x, then we'll be good. So let's try to do it. And this is something that we've done several, times before. So absolute value of x, you can rewrite that as absolute value of a minus x is greater than or equal to absolute value of a minus absolute value a minus x let's see, as long as this quantity is less than a, then the whole thing will be positive. So let's be hopeful and just write that down. Since absolute value of a minus x is less than a, and that in turn will be greater than absolute value of a minus delta. And I want this to be like bigger than a positive constant, and I'm allowed to choose delta. So if delta was, say, absolute value of a over 2, that would be helpful. So let's go ahead and say that. That's bigger than or equal to absolute value of a minus absolute value of a over 2, which would be equal to absolute value of a over 2, since delta is less than or equal to absolute value of a over 2. So that gives me a constraint on the delta that I need. So let's let delta be the min of absolute value of a over 2 and something else. The something else will probably depend on epsilon. So this should have been given more space. It will be given more space in the notes that you get. So that gives us a lower bound. Absolute value of x is always bigger than or equal to absolute value of a over 2. So what do we get? What we have so far is from 3.17. There's 3.17. We have the thing that we want to be small is less than delta divided by a times x. But we know that x is less than absolute value of a over 2. So this whole thing will be less than delta divided by a squared over 2. Oh, neat. So there are no more x's left. I can set this equal to epsilon and solve for delta. So let's do that off to the side. And I won't use equal because I already have some constraints. A squared over 2. I need that to be less than or equal to epsilon. So I can multiply a over 2 to the other side. Delta is less than or equal to epsilon times 2 divided by a squared. And if I arrange that, then this will be less than or equal to epsilon. So that gives me the other constraint I have in my delta. Delta is the min between a over 2 and 2 times epsilon divided by absolute value of, divided by a squared. Oh, cool. So that gives me the whole proof. Thus, for every epsilon bigger than 0, there is a delta bigger than 0, namely delta equal to the min of absolute, not absolute value, just a over 2, and epsilon times 2 divided by a squared, such that if the absolute value of x minus a, then the absolute value of 1 over x minus 1 over a is less than epsilon. This function is continuous. So the last thing I'm going to do before I stop this video recording is point out that let's look at this choice of delta. Does that choice of delta depend on epsilon? Yes. Does this choice of delta depend on a? Double yes, in two different places. So this delta depends on a, which is fine if you're interested in continuity, but that's something that's worth pointing out. Let's do this next one. The sine function with a g is continuous on our away from 0. So if you want to prove that, well, let's do it. Let's consider any a in r minus 0 and any epsilon bigger than 0. So let's just draw a picture and try to come up with this choice of delta. So scratch walk, here's a picture of the graph. And you do have this picture of what continuity is supposed to mean, right? So you consider this point A in the domain, or maybe A is over here. It's color-coded. A is over there. So then f of a, g of a is up there. If you want it to be continuous, you need to say for any epsilon, so let's draw an arbitrarily small epsilon neighborhood up here. And then you want to say as long as x is close enough to a, then g of x lies in that neighborhood. Oh, but that's like easy, right? It looks like any x value that's positive will do the trick. So let's see, how far to the left could we go and still be okay? Well, let's just draw it and see. So let's just let x's start traveling to the left. It looks like if I consider that x value, that's bad. G of x is not very close to G of a. It's not within that epsilon neighborhood that I've drawn. So how far did I go? It looks like as long as I went less than a distance of a, then I'm fine. If I go right, then it looks like I'm fine forever. And the same thing here, except instead it looks like I can go right by negative a instead. So let's consider any a in, that gives me a choice of delta. Looks like delta equal to absolute a should do the job. If you're feeling novice, maybe divide by 2. So let's see if the proof works. So let's consider any a in r minus 0 and any epsilon bigger than 0. Since a is not equal to 0, absolute value of a is bigger than 0, I will let delta be the absolute value of a. Divide by 2 if you want to. So let's assume that x is in r minus 0, and assume that absolute value of x minus a is less than delta. Let's solve that inequality for x and substitute in the choice of delta. So what my goal is to show that if a happened to be positive, then then x would also be positive. So then g of x and g of a would both be 1 and we'd be done. If a happened to be negative, I need x to also be negative. So let's do that by just, I guess, saying everything that I can about x. So let's solve this inequality for x and see what happens. So let's see, negative delta is less than x minus a is less than delta. So solving for x, looks like I get a minus delta is less than x is less than a plus delta. And I know that delta is equal to the absolute value of a. So substituting in our choice of delta, it looks like I get a minus absolute a is less than x is less than a plus absolute a. In the case that a is bigger than 0, let's use that to show that x is bigger than 0. Since a is bigger than 0, absolute value of a should be a, I guess. So 3.19 becomes 0 is less than x is less than 2a. In particular, x is bigger than 0. So remember that this g of x is the sine function. So since x is positive and a is positive also, it looks like I get absolute value of g of x minus g of a is equal to 1 minus 1, since x is bigger than 0 and a is bigger than 0. That's 0, which is less than epsilon. That makes me happy. Suppose that a is less than 0. Let's study that. Since a is less than 0, absolute value of a is negative a. So equation 3.19 becomes (2a is less than x is less than 0). Right, I'm looking right there. In particular, x is less than 0. Now we can conclude that the absolute value of g of x minus g of a is equal to absolute value of negative 1 minus negative 1, since x is less than 0 and a is less than 0. This is 0 is less than epsilon. Thus, either way, we see that absolute value of g of x minus g of a is less than epsilon. And summarizing, let's put the summary right here. Thus, for all a in R minus singleton 0, did we start by considering any a in R minus singleton 0? We did. That's good. And for all epsilon bigger than 0, because I also considered any epsilon bigger than 0, Then I came up with a choice of delta. There exists a delta bigger than 0, namely delta equal to absolute A, such that for all x in r minus singleton 0, if the absolute value of x minus a is less than delta, then the absolute value of g of x minus g of a is less than epsilon. And so now let's again notice our choice of delta, delta equal to absolute value of a. Well, somehow it's independent of epsilon, which is interesting, but it does depend on a. It definitely depends on a. So these proofs above give a function delta which depends on both a and epsilon. And just take a look at the both of them, delta equal to absolute value of a. As a goes to 0, that definitely gets small. So in that case, yeah, limit as a approaches 0, delta a comma epsilon is 0. Let's look at this one. So let's see, as a approaches 0, a over 2 gets small. On the other hand, as a gets small, 2 epsilon over a squared gets really, really big, which is, interesting. So the min between a number that's really, really small and a number that's really, really big is small. So yeah, that delta still gets small as a gets close to 0. And so it looks like in each of these cases, the limit as a goes to 0 of delta of a comma epsilon sure looks like it's 0. And that's suggestive that this delta can't be taken to be a constant, because at least the proofs that we gave require deltas that get very, very, very small close to some limit point a. So if we want to be able to pull off a proof that used the same delta all the time, the deltas would all kind of have to be uniformly big in terms of a, and these ones aren't. So these two things are the prototypical non-examples of uniformly continuous functions. Now, let's actually give the honest-to-God definition. Let f from u to r be a function. F is called uniformly continuous on u if for every epsilon bigger than 0, there exists a delta bigger than 0 such that for all x and a in u, and you know what, it doesn't matter what the variables are called, but just for symmetry, for all p and x in u, if the absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. It doesn't matter what the variables are called, but well, so check it out. What things can this delta depend on? Only epsilon. So that means that you have to use the same delta for every x. This delta is uniform in x. Cool. So I'm going to stop within a minute 15. I'll just tell you what the next video will start by doing. We just found some proofs of continuity of functions, and the deltas that we found in those proofs depend on a and on epsilon. That doesn't necessarily mean these functions aren't uniformly continuous. That just means that the proofs we found don't prove uniform continuity. The first thing I'm going to do in the next video is prove that the two functions that we just talked about are not uniformly continuous. I might even suggest, before you even watch these videos, make an attempt at going through those proofs. Groovy. I'll talk to you in a bit.